Smart Chem, what do? We make a new class of semiconductor polymer transistors that are particularly used to drive the next generation of displays. We actually manufacture them as inks, so they are low molecular weight. Sometimes the inks are used as single layers, as dielectric layers. They're used to make RDL layers. Sometimes they're put into a stack, think a stack of pancakes, and etched to make transistors. And sometimes those inks are actually poured on top of existing display infrastructure that allows you to build displays in reverse. What's unique about what we do is that we make these transistors at extremely low temperatures by comparison with, and so we're talking display transistors. So we're not talking silicon transistors. So we're talking making transistors by the square yard, not on silicon disks. So today there are three major processes: LTPO, LTPS, IXO, and amorphous silicon that drive different types of displays. They're all high temperature processes, and that's very energy, uses a lot of energy and a lot of expensive material, a lot of expensive capex. Our materials are processed at less than 100 degrees, and they are all low molecular weight, so they can be used for conventional spin coating and slot die coating, and in fact even be some of them are actually being used at the moment in printheads. So in order to get a new material actually adopted, and I'll talk about materials a little bit more and what they are shortly, but it's not just enough to make the ink and then say to the world, no, here, you all use it, and this is more or less what it does, and find the applications. And we learned a lot from the silicon industry, and the silicon industry says we've got a whole bunch of new materials. In that case, it was silicon and some of the ion implantations, but you also needed to have design tools so that you can access the brain's trust of all of those people at UMass and many other universities and in all of the industrial base who want to design a circuit. And they want to use the standard design tools that are available today from people like Cadence and Synopsys. And I'll tell you what we're doing in that respect. And then you need to have independent foundry services where someone can take that design and actually can get that design made. So we're a materials company. We actually want to sell our materials to the foundry service. So in order to achieve that goal, we have to do not just generate the actual materials themselves, we have to enable people the skill sets to be able to use them, and we have to enable a third-party foundry service. So this sort of repeats what I said. You know, we make inks that we sell them in bottles. You know, think bottles of well, mostly perhaps single cream would be the viscosity of them. We do sell actually single layers of our polymers. It was not something that we set out to do. We set out to just sell stacks into transistors, but we have found that they have some, you know, the low processing temperature and the fact that they are all photo cured allows people to do redistribution layers. And somebody asked earlier about using stretchables for making multiple layers. So we can make multiple redistribution layers for PCBs. And then we have the organic semiconductors, and then we have the process, because it's not just enough to sell the materials. You've also got to you also have to develop the process by which they are used, and define and it's not enough just to say, well, you use UV light to cure them. You have to have the dosage rate. They have to work on different machines. They work at different scales, different sizes. So it's quite an effort to develop the processes. I'll digress to a very short story. When I took over as the CEO of the company, we'd just sent our organic semiconductor to a Taiwanese manufacturer who had processed it down their line, and it came back with the note that said it didn't work. So we did our failure analysis, and the very first board meeting I sat in on, somebody said, well, guys, it doesn't work because there's none of it left. And of course, the first thing they did in an inorganic line was remove all the organics. So they put an organic stripper down. The first thing they did, or the organic stripper, dissolved it all. So we actually had to redo our polymers in order that they would be resistive to the type of organic strippers that are used in inorganic lines. Quite a challenge, but we actually did it. But it's a good example of, if you want your materials to be adopted, they have to work on existing infrastructure. This is, I told you, think a layer of pancakes. We start with a substrate, do a base layer. We put our organic materials down. We put our source drain gates, the insulators. Then the second thing that we actually found was that, of course, people want to sputter metals on top of these things to connect them all together. And organics aren't very good at having things sputtered on top of them. So we had to develop, another layer in the stack that actually was sputter resistant, so that we could then actually sputter the materials, make the top gate. And then, having done all of that, we then had to make a passivation layer that actually sat all over on the top of the whole thing. So we've developed our materials. We started an internal project to be able to develop the EDA tools. We did that in conjunction with the University of Barcelona in Spain. And we've now actually funded a multi-year program with them. And they've spun out a startup called FlexiIC that is making some open source EDA tools. So if any of you actually would like to get something designed, these guys will design it for you. And then I'll tell you how you get it made. So we've got to the point of the very first process design kits that can be used in our prototyping fabs. Shortly, and I'll tell you about in a minute, we'll have a foundry service, and the tools there'll be a new release of the tools that are matched to that particular foundry. In terms of foundry services, the gold standard around the world for semiconductor foundry processes is ITRI, the Industrial Technology Research Institute in Taiwan. They're the people who, from whom spun out TSMC, the world's largest semiconductor company. And we now have a multi-year program with those guys, and they are putting our organic thin film transistor process on what's called a Gen 2.5 line. A Gen 2.5 builds panels about this size. Absolutely crucial for our development, because and again, it's great having a new material, but if you go to any of the big panel makers, people making these sorts of displays, AUO, Innolux, Samsung, LG, and say, I'll tell you what, could you just take our materials and try it on your line? And they're going, well, it's $20 million a day coming off that line. If you close our line down because it sputters on something and messes us up, close one of our machines down, and we can be it's millions of dollars we'll lose. And of course, many of them don't have, they built up these lines, and if they're adopting a completely, and all they're interested in doing is refining them now. They're not interested in adopting a brand new technology unless it's demonstrably compatible with the equipment and the processes that they have. And so for us to, I'm going to say, be chosen by ITRI, but it's a genuine partnership. They were looking for next generation transistors, and and we've been working with them for a while. And so we've now a formal multi-year contract agreement with them, and by the It depends who you ask. If you ask my CTO, he said at the end of the year, if you ask me, it's end of September, we'll have a fully qualified process at Gen 2.5 in Taiwan at the ITRI's facility that other foundries and customers can use for prototyping, but more importantly, they can come and train people. They can evaluate whether this is going to be compatible with their bigger lines at Gen 4.5 all the way up to Gen 10. So, for those of you who don't know, sort of Gen 4.5 is producing things roughly 1.5 meters by 1.5 meters square, and Gen 10's producing obscene things, which is sort of 3 to 5 meter squares of transistors. Again, as a bit of a sidebar, we think about the silicon industry as being, this huge industry that produces millions and millions of square inches of transistors. The display industry produces 15 times as many square inches of transistors as the whole of the silicon industry. One Gen 10 plant in Shenzhen will produce the same number of square inches of transistors as the whole of the silicon industry. So we're at a different scale. Equally, we're producing, on a panel this sort of size, maybe 10 million transistors, and they're producing 100 billion on a square inch. So very different areas. This, however, is absolutely crucial to the development of our company. So how are we doing? Well, our planarization materials are being used to cover thick copper tracks. Our low temperature is being actually used to process on top of directly on top of LED wafers, and we've taken those two things where we demonstrated the world's first monolithic micro LED display, and we've turned that into a process that we call chip first micro LED manufacturing. You may have heard lots about micro LEDs being the next generation of display, and they are going to be the next generation of display. They last longer, they use less power, and ultimately you can make them for a lower cost. There are, however, serious manufacturing issues that need to be solved, and the biggest of those is if you think a sheet of micro LEDs, 24 million of them, and you think a sheet of 24 million transistors, and these things are a few microns in size, and you need to put one sheet on top of the other, align them all precisely, and then in today's state of the art is to laser weld them all together. That's a bit of a nightmare process, and people are really struggling to make it yield. And so we had the idea that we would actually turn the process upside down, and because we can solution coat at low temperature without destroying the micro LEDs, high temperature process will destroy your micro LEDs. A low temperature process doesn't. We're actually able to solution coat our transistors directly on top of an array of micro LEDs. So in the top right there, you see we take a transfer sheet, and instead of putting the having to put the electrodes of your micro LED down on top of the transistors and laser weld them, we turn the problem the other way up. So we actually put the micro LEDs face down on the transfer sheet with the electrodes up, and then we solution coat the electrodes directly, the transistors directly on top of the transistors, completely eliminating the need for any welding, because all the connectivity is done using readily available and very well proven via technology. Thank you for the to the silicon industry. So we put our redistribution layer on, we photo pattern the holes, we etch the vias, we metallize the vias with our sputter resistant layer, and then that gives us the basis on which we can simply solution coat our transistors directly on top of that. And so we've just been at SID, and what we were demonstrating here is a variety of different displays where we have coated these are all face down. So what you're actually looking at here is the leakage from the back of we designed a little bit of leakage around the edges so you could actually see it. The light's actually going down into the surface. And we have a variety of different patterns. But what you'll notice is you're not missing any pixels. And none of these have been through any repair loops at all. So we're utilizing the photolithographic connectivity that's available from the silicon industry, using our redistribution layer, which is a solution-coated polymer. And then the fact that we can process at very low temperatures to build the organic thin film transistors directly on top of that. And we're now scaling this process in Taiwan to make bigger and bigger and bigger displays. I don't know if that one's actually going to. So again, we're just showing different, and I don't think this. I'm sorry. You would have something which is dazzlingly bright. Perhaps somebody pushed the button, decided it was too bright for what we're doing. But it works. We can scale it up to 1,000 PPI. That's more than enough for high definition television. It's not enough for AR displays and the sorts of things that you'll see in your that people are trying to do. And great for a watch, great for a monitor, great for big scale TVs, big scale signage, and those are the markets that we're aiming for. We're selling materials. We want square meters of displays and little 3 by 5 millimeter displays that go into AR sets. Somebody said to me the other day, who makes a machine for making some of these things, it's great, Ian, but I can only sell 2 machines, and with those 2 machines I can actually produce the whole of the world's forecast for AR displays, and that's not a business that they wanted to be in. It's not a business that we want to be in. So that's us. We have ship first active matrix micro LED in process development. We can use glass or plastic. We can use make low cost scalable transistor processes. So we have talked to some of the automotive people. You saw the previous speaker talk about making big panels. We can put our transistor arrays on large scale flexible substrates, so you can mix and match whether you want to put an LCD panel, whether you want to put some sensors on, and more importantly, you can produce it on big, by the square yard, which is what automotive wants. And we use standard standard photolithography equipment with a electrical connection that's guaranteed, because it's no longer done by laser welding with the yield issues that goes, because it's actually done using VIA's high yielding process and low cost. We've got a minute before we have to rush for our coffees. Any questions?
Thank you. Have we got any questions?
Coffee beckons then. Hold them all up. Yes, sure.
So I very much appreciate your discussion on developing the process. With these third party, like so the ITRI, do they actually share what they are doing to your material?
Oh no, so we have a facility in the United Kingdom, which is a prototyping facility where we have developed the process. They're scaling it from our 4-inch. We've done up to 8-inch. They're now doing Gen 2.5. That has different challenges. But we have our engineers working in their facility with their engineers. And when a customer comes, the customer comes to that line through us.
Oh, okay, yeah.
And
So it's
then
very difficult to solve a problem if you don't know what someone's doing to your material.
it's impossible to solve a problem unless you, and in fact, my little tale earlier, where they use an organic stripper. If we'd known that before, we wouldn't have sent the material. Well, we might have tested it differently.
There was another question?
Thanks, Ian. Great presentation again.
Thank you.
So my question is on the LED, micro LED solution. So you're showing that the LEDs are shining from the back, or the way it's built. So is it a transparent substrate, or they moved on a sapphire? Is that how the micro LEDs are built?
So the
Right now,
micro LEDs are grown on a sapphire,
Yeah.
then they're put onto a transfer film
Okay.
because they're at too high a density there.
Yeah.
So these things are, 20 by 30 microns,
Yeah.
and you want to place them at 100 microns.
Yeah.
Because sapphires are too expensive.
Yeah.
So you put them onto a transfer film with pads up. You then space them out.
Okay.
And then you take them back onto actually a thin layer of one of our materials that then sets them all in place. So they're put on a post-it note, a layer of sticky, and then you process on top of that, and then you peel that off so the light comes straight out.
Okay. And then you're building the TFTs directly then on
And
the
the
last.
TFTs are built directly on top
On the
of the
last.
contacts.
Yeah.
It has the advantage that you don't have to develop your TFTs for a particular size of micro LED. Those are independent streams joined together by this metallization layer.
Right. Thank you.
It's time. Coffee.
Zero.
Thank you very much, Ian.
Pleasure. Thank you.
Closes this first second.